Welcome to a new video of the inference subject. Today we are going to briefly see topic 3, experimental design. So I hope that it's useful for you. And let us go with them. Let's go with the slides. So here are the slides. Basically, this is a theory topic. So no problems about this topic, but there are like two or three things that you need to understand to better study topic 4. So first of all, what is a model? Well, we are surrounded by models in real life. There are models everywhere. Not all, there is in fact a quote that says that all the models are wrong, but some of them are useful. So for example, at the left, we see a model that it's obviously wrong about the map of Europe, but it was manageable and it was useful for the people in that era. So this is an example of a model that it's not realistic, but it's simple. And we can compare with the model in the right, that it's not simple. In fact, it is a complex model, but it is more realistic. So this is what we are always going to find with the statistical models. In this subject, we are going to see a model like the one in the left, the multiple linear regression model. The multiple linear regression model, it's obviously not realistic, but it's going to be really easy to use. It's going to be manageable in comparison with machine learning models that you will see in the following subject. So in real life, we should deal with this trade-off, and in some occasions, the multiple linear regression that we are going to see in topic 5 and advanced, it's a manageable model. With these models, we are always measuring correlations. We are not measuring causality. And the difference is obvious. You can see it in the picture in the right at the top. Okay, it's obvious that 100 of people who breathe die, but breathing is not the cause of dying, obviously. Okay, so we must not confuse correlation with causation, because there is lots of fallacies online, in newspapers, by politicians, almost by everyone, trying to convince people that something is the cause of another thing when there are only correlations. So previously of using the multiple linear regression model, it's really useful to know how do scientists design experiments. And always in science, everything begins with a research question. The research question is basically linked to the random phenomenon that we have seen in statistics the previous year. Okay, we are trying to know the underneath how does a random phenomenon works. So in order to do so, we just out of curiosity, tell us ourselves a research question. Like, for example, is there a relation between the level of robotization in a country and the employment rate? Okay, so this is an example of a research question. These research questions are done in all the fields of science, including physics, chemistry, but also business and finance. Okay, so this is important for you because of that. Linked or associated with a research question, we do always find a research hypothesis. Okay, that it's basically what we want to show that it's compatible with the current empirical data that we observe in reality. Okay, so for example, there is no relationship between the employment rate and the robotization index in the country. Okay, so if we want to prove that this research hypothesis is compatible with the empirical evidence that we see in real life, we need to gather data. Okay, and we are going to see a procedure that gives us a probability that this research hypothesis is compatible or not with the data. If this probability is too low, we are going to reject something that is going to be called the null hypothesis and accept the alternative hypothesis. Okay, and this probability is going to be the p-value. This is what we are going to see in topic 4. So topic 3 and 4 are basically relating because of that. But previously of computing the p-value and see a statistical hypothesis contrast, statistical hypothesis testing, that is what the tool that we use to falsify a hypothesis and to reject it, we need to know how do scientists design experiments, okay? Because there are lots of corruption. It's really easy to make an experiment corrupt. And if we want to make it correct and we want to prove that our experiment, that people can trust us, basically, okay, we need to be sure that we do an experimental research design. This is the first thing that we need to take into account. Basically, and to summarize everything, experimental design is just dividing two groups at random, two or more groups at random. Okay, it's necessary for them to be at random and for the experimenter to not know which subject goes to which group. Okay, so at random and blind for the experimenter. And then we need to, for one group, we need to make a stimulus in one group, like, for example, giving a drug making the group see an advertisement, and so on. And the other group, we need to make as well another stimulus, but a placebo. Okay, why? Because we want to measure causation here. And the only way to measure causation in reality is through experimental designs. Okay, so we need to make a trustable experimental design dividing two groups at random. Okay, so two groups at random, we apply to one of them, we apply a stimulus, to the other one, we apply a placebo, and later on we observe. Okay, we observe, for example, does the people who has seen an advertisement consume more product than the other people who hasn't seen the advertisement? Does the people that drink coffee run with a better performance 1,000 meters than the people who haven't drunk coffee? Okay, so the people who haven't drunk coffee, for example, you give them a placebo that it's identical to the coffee, but they are not aware that it is not coffee. Okay, so it is impossible to know whether it is coffee or not. So these are examples of experiments, basically. Okay, so we can make one group, we can make several groups. It depends on what on the research question that we are trying to answer, on the research hypothesis that we are trying to validate. Okay, so it basically depends on that. And then we measure the dependent variables. How can we measure? Okay, for example, the mean time that the people run 1,000 meters. Why? Because if we know the mean time or the median time or whatever the statistic, and we also know the sample size, then we are going to be able to apply a two-mean statistical test that is what you are studying currently on topic 4. So it's just because of that, okay? Because later on we are going to make that test and we are going to see whether the product is working or not, whether the marketing campaign is working or not, and so on. So things can go wrong. Yes, several things can go wrong. Obviously, if all the people that are on the random group 1, for example, are men, and all the people that are in the random group 2, for example, are women, okay, we are going to have what we call a contaminating variable. Okay, the cause of the performance is not going to be the product, it's going to be another variable. So we need to be sure that there are no contaminating variables in our experiment, because the cause will not be the product, but another factor, okay, another contaminating factor, basically. Experiments, usually, some of them are not just running 1,000 meters and end of the story. Some experiments are last a year, okay, a whole year. So when people are abandoning the experiments, we talk about mortality. It's not that the people die, okay? It's not the death of the people. No, it's just that the people are abandoning the experiment. We need to also take into account the selection bias, okay? That it's what happens when the experimenter chooses the people, maybe unconsciously, okay? But we do all have biases, and we need to get sure that the political biases, ideological biases, and so on of the experimenters do not contaminate the experiment, okay? That it's something that in practice happens a lot of time, okay? So maybe not just hiring one experimenter, but several of them, or maybe the experimenter that has came up with the research question, it's not working on the methodology. That is what we are calling the triple blind. Okay, the triple blind is when the experimenter is not aware of how the experimenter is going to be done. Okay, it's only aware of the research question and the research hypothesis. This is the best way to do an experiment. However, it's very expensive. So most of the times we just do a double blind mode, that it's a researcher and the patient do not know the assignment group, okay? Just to make this not corrupt, okay? We need to be sure that the experiment is not corrupt. And I do not recommend you to make simple blind experiments, okay? Because it's really easy to just trick the data with simple blind experiments, just the patient knowing which group has been assigned on and so on. So I just recommend you the double blind. This is also important, okay, how to achieve internal validity, but I'm just happy with you to do a random assignment of each patient to every group, okay? So two groups are random and not with matching, okay? Because with matching, yes, we are sure that maybe there is a 50-50% of men and women and in every group, okay? But if you hire enough people with an experiment, just as random, these distributions are going to converge to 50-50, okay? So I just recommend you to do random experiments, okay? We follow this notation. R is random, okay? Random group 1, random group 2. The X is the stimuli. Okay, so in here in the random group 1, we do a stimulus to this group, and to random group 2, we don't do an stimulus to this group. And finally, we observe some variables. Okay, so this is the way of making experiments. This is an experiment, the one that it's on bold type. This is the experiment. This wouldn't be an experiment because groups have not been split at random, and this is also not an experiment because there is only one group. Okay, so basically, in order for an experimental design to be correct, we need to be sure that there are at least two groups. One of them receives the stimulus and the other one not, because this is going to create the experimental group, the control group, and then we are going to apply the tools of topic 4. Okay, this statistical test of two means or of two proportions to see whether the stimulus is having effect or not in one of the groups. Finally, important, when we make an experiment, and most importantly in business, in finance, in marketing, and so on, we cannot generalize the conclusions of the experiment across situations, across time, across individuals, across countries, and so on. Why? Because the customer behavior is strongly dependent on cultural factors, on time factors, and these things are not going to generalize. So it's very important to think about which is our target population, okay? Because experiments are really expensive, and to put all these things in the report, okay? Because if we do not do that and we make generalizations, our strategical moves in the company, they're just not going to work, okay? For example, Coca-Cola may be useful in Spain, but if we just do the same experiment, I don't know, on China, well, things maybe are just not going to work. Okay, so we need to take that into account when we make experiments, and this is commonly referred as external validity. Okay, so to sum up, we have seen how do scientists make experiments with a small focus on business and marketing. Okay, we begin with a population. Then we just sample a representative sample, sample random sampling, okay, where everyone has equal chance of belonging to experiment. There are not selection biases by the experimenter or by the people that are going to take the experiment. Once that we have that representative sample, most of the times, for example, 1,000 people or 200 people, it depends on the details of the experiment. We just split them on two or more groups, okay? If we split them on two groups, we do that split at random. This is really important. And the experimental group is going to receive the stimulus. The control group is not going to receive the stimulus. So we apply the stimulus to the experimental group, and then we measure a dependent variable, like, for example, the performance in 1,000 meters, the sales or the money spent on a certain product by the experimental group who has seen an ad, with respect to the control group. And once that we have these two statistics of position, like, for example, the means or the medians or the proportion about the variable that we need to measure, for example, these people has run the 1,000 meters in a mean of 3.5 minutes, and these people has run the 1,000 meters in 4 minutes. We apply a t-test of two medians that we are going to see on topic 4 to determine whether the research hypothesis that, for example, Coca-Cola, it's a good product to run 1,000 meters faster, is compatible with the data or not. If the probability that the opposite hypothesis that we are trying to validate, the null hypothesis, is really low, it's really low compatible with empirical data, we are going to falsify that hypothesis because it's not compatible, and we are going to accept the null, the alternative hypothesis. And this is basically what we are going to see on topic 4. So thank you for your attention, and I hope that this video has been useful for you. So until the next video, have a good time.